Okay, so let's do this example. So solve the differential equation. Let's say y prime is equal to e to the power of 2x over 5y. Okay, so this is pretty much straightforward. It's like what we did last class. So dy dx is equal to e to the 2x over 5y. You send the y with the dy, the dx with the x's, and so you get 5y dy is equal to e to the 2x dx. Okay, then you do the integral on both sides. So the integral of 5y dy equals to the integral of e to the 2x dx. And that means that 5y2 over 2 is equal to e to the 2x over 2 plus c. Okay, so we could isolate the y, so we will do. Okay, so first I will multiply everything by 2. Okay. So 5y squared is equal to e to the 2x plus, well, 2 times c, I don't care, I'm going to call it c again. Okay, it's a constant, I really don't care. And then I will divide everything by 5, so y2 is equal to 1 over 5 e to the 2x plus c, another constant, right? C over 5, still a constant. And then I will square roots. And so y would be plus or minus square root of 1 over 5 e to the 2x plus c. And this is your general solution. Okay, so any constant that you put here, this function will satisfy this differential equation. Done. Okay, so as you see, separable equations are not so difficult. Initial value problems. So what is an initial value problem? Okay, so an initial value problem. Okay, so some call it IVP. Okay, an initial value problem is just a differential equation. It's a regular differential equation. Is a differential equation with what we call boundary conditions. Okay, so let's explain what is a boundary condition, and to do so, I'm going to give you an example, and then I'm going to explain when I do the solution. I'm going to explain. Okay, so for example, solve y prime is equal to x over y with y of 1 equals to 4. Okay, so it's as you see, a differential equations right here. And now this is what we call the boundary condition. Or also we call this the initial value. Okay, same thing. So basically, what we're going to do is we're going to solve it the exact same way we did so far. But we're going to use our boundary condition, all right, or our initial value, to find what a constant is. What's the constant? Okay, so let's solve it. So
Sir?
y, yes?
Is it y of 1 equal 4?
Yeah, y of y equals to 4. So dy dx is x over y. This means that y dy is equal to x dx. Then we integrate both sides. So y2 over 2 is equal to x2 over 2 plus z. Okay, and if you want, we could do y2 is equal to x2 plus 2c, so just c. And now, I know that, so this is my general solution. Okay, so right here, this is the, what we call general solution. Okay, so I could isolate y. I'm not going to do it right now. Okay, I'm going to leave it implicitly. And now I'm going to use my boundary condition to find what c is. Okay, so y of 1 is equal to 4. That means that if x is 1, y is 4. So 4 squared is equal to 1 squared plus c, and therefore c is equal to 15. Okay, so my solution is y2 equals x2 plus 15. Okay, this is called a particular solution. Any questions? Okay, so in the exact same way as a regular differential equation, separable, right? The ones that we did until here, and you found a general solution. That's what we did last class. And now we have an extra information, which is a boundary condition. In other words, it's a point on this relation, in this graph, right? A point here. That allows me to find the exact solution, okay? When I find that the c equals to c, a equals to 15, sorry. Are there any questions?
So do you leave it like this, or do you put a square root for the y
I
squared?
could leave it like this. You could do plus or minus square root if you want.
Okay.
Okay. You don't have to, unless I ask you to. For example, we're going to try it. Solve the following initial value problem. Okay, so let's say y prime equals to x, x2, and the boundary condition is, or the initial value is y of 0 equals -1. So we proceed as usual. dy dx is xy3 over the square root of 1 plus x2. So the y3 will go under the dy, the dx will go up here. So I'll have dy over y cubed is equal to x over the square root of 1 plus x2 dx. And then I will take, now it's separated, x and the y are separated, I will do the integral. And the antiderivative here is -1 over 2y2 equals, and here if you do the antiderivative of this, you will get square root of 1 plus x2. That's what you'll get. Let's see. You okay with this? Okay, so now we need to find C. So I'm going to apply the initial value. So if I plug in x is 0 and y is -1, I get so y of 0 equals -1, means that -1/2 is equal to 1 plus c, and so c is -3 over 2. Okay. Let's continue here. So my solution will be, my particular solution, -1 over 2y2 equals the square root of 1 plus x2 plus c, so -3 over 2. Okay, let's isolate, so that's my answer. Okay, but I'm not done, I'm going to isolate y. So to do so, I will multiply everything by -2. So I get 1 over y2. If I multiply by -2, I get +3 minus 2 square root 1 plus x2. Then I'm going to flip everything. So y2 is 1 over 3 minus 2 square root 1 plus x2. And then if I isolate y is equal to plus or minus the square root of all this. So 1 over square root of 3 minus 2 square root 1 plus x2. It's okay until now? It's just basic algebra at this point. So one thing here is, how do I know, do I choose the plus or the minus or both? Well, let's go back with my boundary condition. Let's plug in x equals 0, and we should get -1. The y should be -1. Okay? So if I plug in 0 here, I get 2 times 1 is 2, 3 minus 2 is 1, so 1 over 1, I get 1. So, and y has to be -1, so I need to take the minus. Okay? So, for my boundary condition to work. And so my solution will be -1 over square root of 3 minus 2 square root 1 plus x2. That's my solution. Okay, so what's really going on here? Okay, is the following thing. When we solve the general solution, okay, you see this is a bunch of relations, a lot of them, depending on C. Okay, so it should be, so either, I don't know, like this, like this, like this, or another one like this, pluses, like this. I don't know, there's tons of them, okay? Depending on what the C is, okay, plus or minus. When we have the condition 0 minus 1, well, I'm just saying that I need to choose out of all these solutions only the one that goes through 0 minus 1. So that's why this is my particular solution, just this one. Okay? This corresponds to this exact relation. You understand? So this is a general solution right here. And once you incorporate the boundary condition, right away you're saying that your solution needs to pass through this point. Therefore, it sort of crystallizes to this relation only, not the other one. That's the particular solution.